Hey everybody, welcome to Chem 300. This is going to be the first lecture on Chapter 1, The Chemical World. But before we get started, I just want to say hello, I'm your professor, Dr. Laura Gillies-Doherty. I'm really excited that you're here. If you haven't already, please make sure to watch the recording of the introduction and syllabus lecture that we did on the first day of class. There's a lot of important information in there and showing you how to access different course resources. Before we jump into the lecture, I do want to show you just a couple things on Canvas here quick. So I'm going to share my screen with you and we'll check out our course Canvas page. So when you click on our class, you should go to the front page here. And the main parts you're going to be looking at as a student are announcements, shown here on the left, modules, discussions, assignments, and grades. And if you ever want to find other people in the class, you can click on people here to find email addresses and get in touch with each other. So let's go to modules. That's the main part of the class. There's a lot of important information in the Getting Started module. It's where you're going to find the most up-to-date syllabus, course schedule, information on how to set up Canvas so you get notifications when I post something new, a whole list of different campus resources to help you in this class, and a Getting Started discussion where you can go and post questions about just kind of like how to get going in the class, and I'll check it every couple of days and answer them. Then the rest of the course is going to be organized by week. So each week there'll be a new module and it will be broken up into lecture and lab. And this is where you'll find links to any assignments for the week, lecture videos, notes packages, anything to do with that week's class is going to be in that week's module. So we'll have 16 of these by the end of the semester, one for each week of the class. So the first day of class, you click here to attend the Zoom lecture. There's a couple assignments and discussions. And the thing I wanted to point out, because we're talking about Chapter 1 in this video, is the Chapter 1 lecture videos. So for each chapter of the text, I'll have a page where you can click and it will tell you what to do for that chapter of the text. So here for Chapter 1, it says to pre-read or skim Chapter 1 in the online text and jot down section headings and key terms. And then you'll watch the pre-recorded lecture video. That's this. So if you're here, you're in the right spot. And make sure you take notes while you watch. Your class notes are going to be graded in this course, so take notes as you watch the videos. And I give you some hints about what your notes should include to be good notes. Make sure you include definitions and important terms, include key equations, work out every example problem we do in the lecture videos, work it out on your notes pages, annotate those to show how you solve the problem or leave little notes or reminders for yourself. And then at the end of most sections or chapters, I'll have self-study questions to kind of prompt your thinking and explore the subject a little bit deeper and check for understanding. So also answer those in your notes. All of my PowerPoint slides are going to be online for you to download. I'll link them on the lecture videos pages, and I might also just put those directly in the modules. We'll see what works out best for our course organization. But you can always download the PowerPoint slides and use them as you watch the videos to follow along. You could take your notes directly on them if that works for you, or some students just like to look at them afterwards, because I know I tend to go pretty fast. We have a lot of material to cover, and so they'll check the PowerPoint slides to make sure they didn't miss anything important in their own notes. Then you want to review your notes shortly after taking them. The same day is perfect. You want to wait, 20 minutes to an hour and then review them. And that's a way to check that you understood what you were taking notes on. If you review them and it looks like a foreign language, then that's a clue that you need to go back and potentially watch that lecture video again or adjust your notes. At this time, jot down any questions or trouble spots as you're reviewing your notes so that when you come to the lecture in person, where we're going to work on homework problems and practice problems, you're ready to ask questions about the lecture that you just watched. Okay, and so then just down here, the link isn't here yet because I'm recording it right now, but this is where I'll put the links for the Chapter 1 lecture videos. And I'll do this for each chapter. So as I generate the videos for our course, there'll be a page in the module for that chapter, and then it'll tell you what to do, and then there'll be links to each of the videos. Okay, the other thing I wanted to show you is our online textbook. It's free. It's written specifically for this chemistry class, Sacramento City College Chem 300 by the chemistry faculty. The link to the book is on the course webpage and in the syllabus. You're welcome to read it online. You're going to find this contents button over here really helpful to jump around chapters and expand chapters and jump to the different sections. The other thing that's going to be really useful other than the contents tab is that if you prefer to read a textbook on paper format instead of reading it online, you can go here to the PDF button and you can download the entire textbook so that you can read it offline. You could print it, you could write on it, you could highlight it, whatever you want. If you want to purchase the textbook, if you want a printed copy instead of printing it yourself, you can buy a paper copy. It takes you to the LibreText bookstore, and it costs about $24 to buy a paperback cover of our textbook. Or if you want the hardcover, you pay $8 more. There's a little bit of shipping associated with it. So print copy, about $30, including the shipping. Okay, so those are some textbook options. Again, you can download the PDF of the entire book. You're welcome to read chapter by chapter online. Use the table of contents here to navigate. And you can also purchase a print copy if that's what works better for you. Okay, so let's start talking about some chemistry. Jump over to PowerPoint. So we're going to start out talking about the chemical world. You'll see in my lecture videos, I always say hi and let you know that I'm alive. And then I usually turn off my video because I personally find it kind of distracting while lecturing, but I always do start out by saying hello, and that is nice to see everybody. Okay, so this is chapter 1. It's an introduction to the chemical world. What is chemistry and the scientific method? So chemistry is the study of the interactions of matter with other matter and with energy. So you might be saying, okay, so chemistry is the study of the interactions of matter with other pieces of matter and with energy. Well, what is matter? It seems like that's like the heart of chemistry. Well, matter is anything that has mass and takes up space. So it's basically anything that's physically real, anything that has mass and occupies some space. So like steel, water, wood, plastic, these are all types of matter that are visible to our eyes. But there's other types of matter like air, microscopic dust, viruses, bacteria, teeny tiny things that we can't see without magnification, and those also count as matter. And the really cool thing is that because matter goes all the way down to individual atoms and subatomic particles, and then these parts combine, like the parts of an atom combine to make an atom, and then atoms combine to make molecules, and then molecules combine to make bigger and bigger things. And since chemistry is the study of all of this, chemistry is essentially the study of just about everything. Because just about everything is matter, and anything that's not matter is typically energy. And chemistry is also the study of how matter interacts with energy. So it's everywhere, literally everywhere. So matter is composed of atoms. In some substances, like aluminum, for example, the atoms are going to exist as independent particles, just like atoms one by one. And then in other substances, like rubbing alcohol, isopropyl alcohol, the atoms bond together into these well-defined structures that we call molecules. So we'll go into more detail about atoms, elements, and molecules as we get into chapters 2 and 3. But we're just trying to kind of introduce matter here because matter is the heart of what chemistry is. Chemistry is studying matter and how matter interacts with energy and other types of matter. So there's 3 common states of matter. We call these states or phases. That's a solid, a liquid, and a gas. And so we can classify matter according to one of these physical states. Is it a solid, hard? Is it a liquid, right? Kind of moves around to fill a container, whatever shape it is. If it a gas, it expands to fill the whole room. So we're going to go into more details on these different states of matter and how substances transform from one state to the other as we go through the course. So because chemistry is the study of matter and how matter interacts with other pieces of matter or energy, it's central to pretty much everything else in science. And so this is why chemistry classes are oftentimes kind of one of the first classes you have to take in science before you can take anything else, because everything connects to chemistry, because chemistry is the study of matter. Everything around us just about is matter. If it's not matter, it's usually energy, and chemistry is also the study of how energy and matter interact with each other. And so that's why chemistry classes are so important, because based on what you learn in chemistry, you're going to build and connect that to things like physics, biochemistry, biology, medicine, geology, geochemistry, you name it. So chemistry is just one area of science. It's interconnected to all the other areas. And science is the process in which we learn about the natural universe by observing things, testing them, and then generating models that explain our observations. So there's several main areas of chemistry. The first is called organic chemistry. Organic chemistry is the study of chemicals that contain carbon and hydrogen. And almost all the chemicals that are found in living organisms are based on carbon and hydrogen. So if you want to study anything that's alive or based on a living organism, plants, animals, humans, you name it, that's going to go into the realm of organic chemistry. Second main area of chemistry is called inorganic chemistry. This is the study of chemicals that are in general not primarily carbon-based. So these are chemicals and substances commonly found in rocks and minerals. It's really important for environmental chemistry, mining. A lot of kind of new developing energy technologies like solar panels use a lot of inorganic chemistry. Analytical chemistry is our third main area of chemistry. It's the study of the composition of matter. So if you go into analytical chemistry or you do analytical chemistry, you're going to be focused on separating, identifying, and quantifying chemicals and samples of matter. You're taking measurements and figuring out the identities of things. If you like CSI, those types of things, that's all analytical chemistry. When somebody goes into a lab and they take a sample, they go to a crime scene, they take a sample, then they take it back to the lab and they run it on some fancy instrument to figure out what it is. That's doing analytical chemistry. Fourth type is physical chemistry. Physical chemistry is the study of macroscopic properties, so like kind of overall properties, atomic properties, so at the very small level, and these phenomena, how they interact in chemical systems. It's kind of like really advanced inorganic and analytical chemistry combined. And if you are a pre-chemistry major, you take P-Chem kind of more towards the end of your chemical studies because it gets really complex. Fifth type is my personal favorite. It's biochemistry. This is the study of chemical processes that occur in living things. So biochemistry is based on living things. So you have to know a lot of organic chemistry to do biochemistry. But instead of just studying individual molecules and atoms that involve carbon, you're studying kind of the whole system or the whole process. And then the sixth type, and this one was not mentioned in your textbook, but it's a really important area of chemistry, is nuclear chemistry. So nuclear chemistry is the study of the changes or reactions that take place inside the nucleus of an atom. And these changes or reactions that happen inside the nucleus of an atom are capable of releasing extremely large amounts of energy or even changing the identity of atoms. And so we use a lot of nuclear chemistry and nuclear medicine. So for example, like PET scans and CT scans, those rely on nuclear chemistry, radioactive elements being used to image medical conditions. And radiation therapy is used as a medical treatment for many types of cancer, and that's all nuclear chemistry. So these are our 6 main types of chemistry. So I've got a video talking about what is chemistry in these 3 main types. Let's check it out.
What is chemistry? Chemistry is the science of matter. This may sound simple, but chemistry is a complex and broad topic that covers a wide variety of fields. From the core of the Earth to the farthest reaches of the universe, chemistry is everything and everywhere. Chemistry, a definition. Chemistry is the study of matter, including its composition, properties, and structure, how it changes, and how it interacts with energy. This is a pretty simple definition that sums up what is actually a complex and fascinating subject. If you have ever asked why or how something is in the natural world, odds are good that your question and the answer were related to chemistry. For instance, why is the sky blue? Colors depend on the chemical makeup of substances and what kind of light they reflect. How does an insect walk across the surface of a pond without falling through? The unique properties of water give it a high surface tension, which means that small objects can rest on it without sinking. Chemistry is all around, and anything related to matter involves chemistry. Main branches of chemistry. Since chemistry is such a broad and vast subject, we can divide it up into more manageable topics to help us more accurately. 1. Organic chemistry. 2. Inorganic chemistry. 3. Analytical chemistry. 4. Physical chemistry. 5. Biochemistry. We will learn more about these topics as we go on.
Okay, so that was a quick kind of repeat of the main areas of chemistry. And I love teaching chemistry, especially this class, because literally like we've been saying, chemistry is everywhere, connects to everything. It's why I went into it, because I'm the type of person that isn't happy with kind of a general answer. I kind of want to know the details and why things actually work the way they do. And chemistry is a field that can answer those types of questions. So we're next going to talk about the scientific method. This is how we do chemistry and how we do science. And so chemists learn and make discoveries by making observations, forming a hypothesis, and asking questions, and then performing experiments to produce new knowledge. And so this process is called the scientific method. And kind of one of the main things I really want to emphasize with the scientific method is that it's a process. It's not a one-way street where you go from start to finish and then you're done. You'll see that there's a lot of loops in the scientific method where things need to be repeated. They need to be modified as new knowledge is gained, as new questions are asked, as new observations are made. We repeat the process over and over and over again. It's never going to be something that's stagnant. And really good science is science that is questioning and pushing the bounds of what we know and kind of asking our scientists to prove it, to repeat an experiment, to prove a hypothesis, to do it multiple times under multiple conditions. And that's just part of the scientific process. So let's start at the top. So you start by making an observation, right? You're curious about the natural world, and you either measure or you observe something in nature. And there's two general types of observations that are made in science. There's qualitative observations. These are observations that don't rely on any sort of measurement. You're just kind of seeing something and making a general comparison. Like it's cooler in the winter than in summer. It's a qualitative observation about nature. The other types of observations are quantitative observations. These are the ones that rely on measurements and numbers. So a quantitative observation might be the average winter temperature is 20 degrees Fahrenheit less than the summer temperature. Both of these observations are observing the phenomenon of seasons, but one of them is qualitative. It's pretty relative. It's cooler in winter than in summer. And the other one is quantitative. There's a measurement involved regarding the temperature. How much cooler is it? So you start by making an observation, and then you form a hypothesis. And a hypothesis is kind of like an educated guess or a tentative explanation, or even a prediction about the observation. So you'd say, I think blank happens because of this reason. Like, I think it's cooler in the winter because the Earth is rotated farther away from the sun. So it's a tentative explanation of that observation. So you're kind of predicting why you think what you observe happens, or kind of asking why it happens. Then after you form your hypothesis, you do experiments. You design a test to figure out if the hypothesis is true or not. And so an experiment is a controlled method of testing a hypothesis. And the controlled part's really important because we have to use systematic observations or measurements. So we usually try to test the hypothesis one variable at a time. You form a hypothesis like it's cooler in the winter because the Earth is rotated away from the sun, something like that. And then you would find a way to systematically test it one variable at a time. Then the most important part is you repeat. Each time you perform an experiment, a test, based on how it goes, what your results show, then you modify your hypothesis, propose a new one to further develop that knowledge. And so you want to repeat this cycle. It's really important in science to repeat the cycle of hypothesis to experiment, and then based on the results, you adjust, you propose a new or a modified hypothesis based on the new information you gained, and then you do a new experiment to keep furthering your knowledge. And you keep doing this around and around and around, hypothesis, experiment, until eventually you have a scientific law or a scientific theory. So I've got another video comparing this idea of a scientific law versus a scientific theory to distinguish between the two. Let's check it out.
Chat with a friend about an established scientific theory, and she might reply, well, that's just a theory. But a conversation about an established scientific law rarely ends with, well, that's just a law. Why is that? What is the difference between a theory and a law? And is one better? Scientific laws and theories have different jobs to do. A scientific law predicts the results of certain initial conditions. It might predict your unborn child's possible hair colors, or how far a baseball travels when launched at a certain angle. In contrast, a theory tries to provide the most logical explanation about why things happen as they do. A theory might invoke dominant and recessive genes to explain how brown-haired parents ended up with a red-headed child, or use gravity to shed light on the parabolic trajectory of a baseball. In simplest terms, a law predicts what happens, while a theory proposes why. A theory will never grow up into a law, though the development of one often triggers progress on the other. In the 17th century, Johannes Kepler theorized cosmic musical harmonies to explain the nature of planetary orbits. He developed 3 brilliant laws of planetary motion while he was studying decades of precise astronomical data in an effort to find support for his theory. While his 3 laws are still in use today, gravity replaced his theory of harmonics to explain the planet's motions. How did Kepler get part of it wrong? Well, we weren't handed a universal instruction manual. Instead, we continually propose, challenge, revise, or even replace our scientific ideas as a work in progress. Laws usually resist change, since they wouldn't have been adopted if they didn't fit the data. Though we occasionally revise laws in the face of new, unexpected information. A theory's acceptance, however, is often gladiatorial. Multiple theories may compete to supply the best explanation of a new scientific discovery. Upon further research, scientists tend to favor the theory that can explain most of the data, though there may still be gaps in our understanding. Scientists also like when a new theory successfully predicts previously unobserved phenomena, like when Dmitri Mendeleev's theory about the periodic table predicted several undiscovered elements. The term scientific theory covers a broad swath. Some theories are new ideas with little experimental evidence that scientists eye with suspicion or even ridicule. Other theories, like those involving the Big Bang, evolution, and climate change, have endured years of experimental confirmation before earning acceptance by the majority of the scientific community. You would need to learn more about a specific explanation before you'd know how well scientists perceive it. The word theory alone doesn't tell you. In full disclosure, the scientific community has bet on the wrong horse before. Alchemy, the geocentric model, spontaneous generation, and the interstellar ether are just a few of many theories discarded in favor of better ones. But even incorrect theories had their value. Discredited alchemy was the birthplace of modern chemistry, and medicine made great strides long before we understood the roles of bacteria and viruses. That said, better theories often lead to exciting new discoveries that were unimaginable under the old way of thinking. Nor should we assume all of our current scientific theories will stand the test of time. A single unexpected result is enough to challenge the status quo. However, vulnerability to some potentially better explanation doesn't weaken a current scientific theory. Instead, it shields science from becoming unchallenged dogma. A good scientific law is a finely tuned machine, accomplishing its task brilliantly, but ignorant of why it works as well as it does. A good scientific theory is a bruised but unbowed fighter who risks defeat if unable to overpower or adapt to the next challenger. Though different, science needs both laws and theories to understand the whole picture. So next time someone comments that it's just a theory, challenge them to go 9 rounds with the champ and see if they can do any better.
Okay, so I like that quick video contrasting and comparing scientific laws and theories. It's linked at the bottom of the previous slide, so feel free to go back and watch it. It's also in the LibreText textbook linked online. So to summarize, a scientific law is really looking at or predicting what happens. It's a statement that summarizes the relationship between variables. And they really give like rules for how nature behaves and what happens based on that repeated cycle of hypothesis and experiment. If you repeat that cycle of a hypothesis, kind of predicting what might happen and then testing it enough times, you can come up with a scientific law that then can be used to predict what happens in that same situation over and over and over again very reliably. So it just summarizes like the relationship between two variables, like the season and the temperature, and explains, just states like what happens. So it can be used, like the video showed, like a machine cranking out data. It can be used to make predictions about what's going to happen based on the scientific law, because many, many cycles of hypothesis and experiment have already been done to test the situation enough to come up with the scientific law. Versus a scientific theory more explains the why behind things. A theory is a model or a well-supported explanation of observations. It's going to give more information about the underlying causes for the observations and the laws. And so theories are always under development. Yeah, you need to continue to perform experiments to further develop the theory to be able to better explain and to explain in more detail what's going on with whatever observation and hypothesis the theory is related to. So a brief summary of the scientific method. Again, you start with an observation about the natural world. You then propose an educated guess or a prediction about why it's happening. It's your hypothesis. You then do a test. You test it with an experiment, and you repeat your testing and hypothesis multiple times, because based on how your experiment goes, if it gave you the result you predicted or didn't, you can ask a new question to better develop your understanding of that observation. Eventually, if you're able to show what happens, that's a scientific law. And if you're able to explain why or develop a model with an explanation, that's a scientific theory. So at the end of each chapter, or for big chapters, a big section of a chapter, I'll have what are called these kind of self-study checks. These are just quick questions to kind of test yourself at the end of a video or at the end of a section or a chapter about the material. So for this one, on your own, define chemistry, define matter, and then in a few sentences, explain the scientific process. Start with an observation and then explain the process that you would go through to end up at a scientific law or a theory and the difference between the two. Okay, that is it for chapter 1, an introduction to what is chemistry, as well as the scientific process. You'll see on Canvas, there's the homework assignment associated with chapter 1. It's to answer all of the odd numbered questions in the online textbook. So check out that assignment on Canvas for more information about doing the chapter 1 homework. Okay, thanks everybody for watching. I'll see you next time.